friends, in the last video we studied about the condition of precipitation, how the solubility product and ionic product affected the precipitation. So in this video we'll discuss the common ion effect and its application. So to understand what is common ion effect, so let us move to the extraction of salt from the seawater nowadays. Okay, so our study is about common ion effect. Okay, so now you see extraction of salt from seawater. In the seawater, you have sodium chloride ionized as Na plus and Cl minus. Why they are not precipitated? So we have already discussed in the last video. So that means their ionic, the product of their ionic concentrations, which is called ionic product, cannot exceed the solubility product. Okay, but if we add concentrated HCl, a large concentration of HCl is added to that seawater, that means now it is precipitated, it is dissociated into H plus and Cl minus. When it was only sodium chloride, the ionic product value was not able to exceed the solubility product. But when you added hydrochloric acid, the chloride ion concentration is now much larger. So what you expected, the ionic product is nothing but Na plus concentration into Cl minus concentration. Due to addition of HCl, the Cl minus concentration is increasing. And now the product that is called ionic product, in the previous case when only sodium chloride was there, now the now the ionic product can well exceed than the solubility product once you add HCl. I am repeating once again and again for your understanding. You see, now when you add HCl, the solubility product, it becomes less than the ionic product, hence precipitation. Are you getting me? So this is the condition of precipitation of sodium chloride. So what did we do? We supplied a compound in which one ion is common. This common ion suppressed the ionization, and due to this higher concentration of Cl minus, which is common, we get a precipitated sodium chloride. So we can take it otherwise that its ionization is suppressed. This case of suppression can be understood by taking another example. You see, the dissociation of a weak acid CH3COOH. The dissociation pattern is like this. When we add CH3COONA, sodium acetate, CH3COONA, it is completely dissociated because it is a strong electrolyte. All salts are strong electrolyte. So CH3COO minus plus Na plus. Now this ion is in common with already present acetate ion. So once the concentration of CH3CO minus is higher, as we discussed in Le-Chatelier's principle, if the product concentration is high, the reversible reaction process in a direction in which the reactant is more prepared, right? So since acetate ion becomes higher, to decrease the concentration of acetate ion, that means the reaction proceeds in backward direction, and once backward direction the reaction flows, that means this is formed more and more, and concentration of acetic acid, that means undissociated acetic acid becomes higher. That means we did not allow the ionization of the that weak electrolyte. So why? Because the common ion is there. We can apply the Lipschitz principle. So this is what we call it common ion effect, in which we can suppress the ionization of a weak electrolyte, or any electrolyte, can say in case of strong electrolyte. That is an indirect phenomena. It's not suppression. But generally, in common ion effect, we just suppress the ionization of an electrolyte by supplying an additional compound whose one of the ion is common with already present ion. Are you getting it now? So this is common ion effect. The application of common ion effect can be seen in the analysis of group radicals. Okay, so let us take the test of group 2 basic radicals in salt analysis, as you do stepwise from preliminary test, then dry test for basic radical, then test for acid radicals, then your wet test for basic radicals. After such steps, you go to the confirmatory test. And in case of wet test for basic radicals, you know the basic radicals, cations, are grouped into that means separate groups, and each group has a different group reagent. This group reagent has been confirmed with respect to the solubility product of various that means group radicals. For example, your cations, the basic radicals of the group 1 are that means precipitated as they are chlorides, because you have to give the group reagent dilute HCl. Are you getting now? So let us now consider the test for group 2 basic radicals. Test for group. Okay. So the basic radicals like Pb2 plus, Cb2 plus, okay, mercuric are the basic radicals in group 2. They are precipitated as they are sulfides. So it is now clear that group reagent is hydrogen sulfide. But the main that is thing to notice is that only these elements, only these cations will be precipitated as sulfide, not other ions. This is not the case. Any ions can be precipitated as they are sulfides. Why they are sulfides is considered because the sulfides of these basic radicals have their solubility product very low. On adding a little amount of H2S gas, the sulfide ion combines with these basic radicals, and now the ionic product easily exceeds the solubility product, because their solubility product is very low, and the precipitation occurs. So to supply a very less amount of H2S, we have to that means make a plan how the sulfide ion concentration inside the solution will be less. For that, when you supply hydrogen sulfide gas, you get 2H plus plus H2 minus. To get this sulfide ion concentration low, you are adding dilute HCl. So that gives you H plus and Cl minus. So the common ion is the H plus ion. So due to this common ion, the reversible reaction proceed in the backward direction. Hence, the sulfide ion and H plus ion combine to give undissociated sulfide ions. So now you are getting a little concentration of sulfide ion. Using that little concentration of sulfide ions, these elements can be precipitated as their sulfides, no other elements. Because these selected elements, there are some other elements also there in the group 2 basic radicals whose sulfides have their solubility product very less, so that on adding a little amount of sulfide concentration from hydrogen sulfide and dilute HCl added together, now the ionic product can exceed easily the solubility product, hence precipitation. And easily these elements are, precipitated as their sulfides. If you are not adding these HCl, the sulfide ion concentration will be more. So even if there is other elements other than group 2 basic radicals, they may be precipitated sulfides. They may look as black precipitate, and that means wrongly you will interpret that perhaps they are group 2 basic radicals, though they are not. Are you getting me now? So that means on minimizing the concentration of sulfide by adding dilute HCl, you are confirmed that only these cations will be precipitated as their sulfides, not other ions. Now it's clear? So this is a beautiful application of common ion. Thank you. We'll discuss in the